Welcome! Have you ever seen an example of the sum of two odd things being odd itself? In this video you will see one. To be fair, I won't be talking about numbers, but about functions. The main purpose of the concept of even and odd functions for today is to simplify integrals. So, what does it mean for a function to be even? An even function is a function whose graph is reflection symmetric in the vertical axis. That is, switching left to right or x to minus x preserves the graph. In a formula, this becomes that f of minus x equals f of x. The standard example is f of x equals x squared. But also x to the power 4, x to the power 6, and any other even power of x is an even function, hence the name. But other functions can be even as well. For example, cosine of x, or indeed cosine a of x, for any value of a. The counterpart to even is odd. What symmetry does the graph of x cubed have? Indeed, it remains the same if you rotate it 180 degrees around the origin. This symmetry is the same as a point reflection for the origin. In a formula, this means that f of minus x equals minus f of x, as the graph on the left is negative exactly where the graph on the right is positive. Other examples than x cubed are x to the power 5, x to the power 7, and other odd powers of x, including x to the power 1 equals x itself. Moreover, sine a times x for any a is odd as well. Note that not all functions are either odd or even. For example, f of x equals 1 plus x cubed is neither odd nor even. Rotating the graph around the origin does not preserve it, nor does reflecting it in the vertical axis. You could see this function as a non-integer function, so only integers are even or odd, but really you should not try to think of even and odd functions as having anything to do with even and odd numbers. You already know how to add and multiply functions. So let's see what happens to even and odd functions if we add or multiply them. As you can see in the picture, x squared minus x to the power 4 is still an even function. Indeed, it is true in general that the sum of two even functions is again even. Showing this is not hard. If f and g are even functions, then f of minus x equals f of x and g of minus x equals g of x. Then also f of minus x plus g of minus x equals f of x plus g of x has that symmetry. Likewise, you find that odd plus odd equals odd, which is a more curious expression, but you can see it happen in the graph of x minus x cubed. Adding an odd and an even function generally gives something that is neither odd nor even. See, for example, the graph of x squared plus x cubed. Now consider the product of two even functions. For example, x squared times cosine of x. Where both functions are positive, their product is as well. And where one function is negative, the product becomes negative. As you can see, the resulting function is again even, and indeed, the product of two even functions is always even itself. If we consider the product of two odd functions, for example x times sine x, the resulting function is even again. Indeed, on the left we have minus times minus is plus, and on the right plus times plus is also plus. Finally, the product x times cosine x of an odd function with an even function is odd. Again, this is very different than the results for numbers, so let me stress again that even and odd numbers are a bad analogy when talking about even and odd functions. So, what is the use of all these even and odd functions? One of the nice things is that you can use the symmetry of the function to aid with calculating certain integrals. This is best illustrated for odd functions. Consider the integral of x times cosine x between -2 and 2. Sure, you can use integration by parts, but look at the graph. The green positive area on the left is negated by a similarly sized red negative area on the right. And likewise, the negative area on the left is cancelled by the positive area on the right. Thus, we see that the total integral equals 0. And the same argument works for any integral of an odd function as long as the interval is symmetric around the origin. The integral from -L to L of an odd function equals 0. For this to work, both the function must be odd and the interval must be of the form -LL, symmetric around the origin. So what happens with the integral of an even function? Take x times sine of x. Then the positive parts on the left of the integral are exactly equal to the positive parts on the right. And likewise for the negative parts. But this means they don't cancel, but add up. As the integral on the left equals the integral on the right, we see that the total integral is twice this. Written out, this means that the integral from -L to L of an even function equals twice the integral from 0 to L of that same function. In class, you will see how you can use these integral identities in a smart way to expand functions in either sines or only cosines. See you there.